In fact, if you go further, you can also have something called electron affinity. And before you do that, let me first write down again epsilon I. So please note how to write epsilon I. Epsilon I is nothing but chi I f chi I. Note that whenever I am calling orbital energy, I have always a reference to canonical Hartree-Fock equation. So that part is clear. Okay? So if I just take the matrix element or expectation value of f with chi I, it is trivial to show that this is called the orbital energy, right? And you can actually write down, you have the matrix element, you have the Fock operator, so you can write down this. So can you write this down? It will become chi I h chi I. So this will help you now to clean up the home assignment very easily after this. Once I am able to write down chi I h chi I plus sum over j chi I chi j antisymmetrize chi I chi j. I hope all of you can show this as well. I will not write anything more because this will be a part of the assignment actually. Okay? When you get epsilon j, you should be able to write this because you have the Coulomb and the exchange operator. I have combined both Coulomb and exchange operator as a chi I chi j. Remember, the sum is only over j. Okay, not over I. I have already repeated because we are talking of a specific epsilon I. And if you also note, our E Hartree-Fock had a sum over all I, chi I h chi I plus sum over I here, but it had a factor half, correct? That is the difference in the Hartree-Fock energy, that you have a factor half, which all means that the E Hartree-Fock cannot be sum of the orbital energies. I have discussed this before also, but let me again repeat it. Because if I take sum of the orbital energies, this sum will come here, here also sum will come, but without the factor half. So I have already repeated that if you take sum of the orbital energies, what is happening is that the interaction between the electrons are double counted. So once you are counting, when you are, let us say you have 2 electron, you are taking epsilon 1 plus epsilon 2. When I take epsilon 1, I take the interaction of 2 on 1. When I take epsilon 2, I take again interaction of 1 on 2. But between 1 and 2, there is only one interaction as far as total energy is concerned. So that is why this factor half is coming here to prevent double counting, and that is the reason the orbital energy sum is not Hartree-Fock energy. I again repeating, because many people have this problem. They get HOMO, LUMO, everything, they just count as a total energy. Hartree-Fock energy is not sum of the orbital energies, and that is very important to realize. In fact, you can very easily show what it is. It is actually sum of the orbital energies minus something. So if I have n electron minus half of sum over ij chi I chi j. That is trivial to show, because if I take all the sum of the orbital energies, the half factor will go. So I have to subtract half of this to get half of this. Okay? So these are trivial mathematics. To show this, you can keep playing around either way. So it is not sum of, so this is the part which is double counted. So this is a single pair energy. A single interaction between I and j has a half factor. When I take sum of the epsilon I, the half factor goes because you are counting it twice. Okay, I on j, j on I. So this is actually a double counting term which is to be subtracted. So, and you can see from the mathematics that if I do epsilon I, I don't have, I have plus 1 here, subtract this minus half of this, you get plus half of this. Okay, is it okay? I think with this background, you should be able to do this quite easily. Remember, you have to use Slater rule to write down En minus 1 Koopmans. That is something I am not going to do. Okay, that is the only part that is missing. And when you do Slater rule, remember the spin orbitals are same. So same chi 1, chi 2, except the chi j won't be there. So when you do these summations, summation will be only over n minus 1 spin orbitals, barring chi j. Right? Otherwise, the Slater rule is same, and you should be able to then subtract and show this. There is only a simple arithmetic. Okay. At the end it will be simple arithmetic. All right. Remember the epsilon I, formula of epsilon I, that is very important. So it says that it's one electron potential plus the sum over J shows that all interactions due to other spin orbitals, Coulomb and exchange, due on I. So that is why there is no summation over I, only summation over J. All right, having done this much, let me now get back to the canonical Hartree-Fock equation and note a very important point, that this is after all an operator eigenvalue equation. Once an operator is defined, I am just calculating an eigenvalue equation. While doing the operator eigenvalue equation, of course, I am doing an SCF procedure. So that is an iterative eigenvalue equation. I guess chi, then construct F, reconstruct chi, and so on and so forth. But it's at the end, it's an operator eigenvalue equation. Given any operator in Hilbert space, we know how many eigenvalues and eigenfunctions are there for any operator. Guess? In an entire Hilbert space, infinity, right? It's an infinite dimensional problem. It is not a 2-dimensional problem or 3-dimensional problem, although I am only interested in n spin orbitals, right? So for the Hartree-Fock, when I do this, I get actually several energies, spin orbitals. I order them as En, then En plus 1, En plus 2, and so on. What I do for obvious reasons, because Hartree-Fock is the minimum energy, and that is very easy to show, that you actually like to take only this part. Now it may also happen that energy is not sum of the orbital energies. So you may argue, why not this becomes lower than this? In some sense, this becomes the Hartree-Fock. Then we reorder. Okay, so that is a little complicated thing. I will not go into that. But for a very standard cases, if the energies are ordered like this, the Hartree-Fock determinant also includes the lowest n energies. But in the process of this solution, I also get this, because it has an infinite eigenfunctions and eigenvectors, right? Eigenfunctions and eigenvalues. So what are the meaning of this? So what do I do with these spin orbitals which are beyond n, whose energies are higher than n, which I am not going to use obviously in Hartree-Fock? So what do I do with those? These spin orbitals from n plus 1 are called unoccupied orbitals. So they will have a very important part in quantum chemistry, particularly when I come to the electron correlation. So they will play a very significant role, and note that together all these orbitals form a complete set of spin orbitals, not just n. So if I have chi 1, chi 2, chi n plus 1, right, whose energies are ordered like this, these together form a complete set. Don't forget this. Just the n will not form a complete set. Although I require only n, because obviously later on I may require a complete set of expansion. So I am just mentioning that all the eigenfunctions of a Hermitian operator form a complete set. And of course, F is a Hermitian operator, which we have already shown. So this together will form a complete set, which will actually include what I now call unoccupied orbitals. So this is the first time we are defining what is called unoccupied orbitals. So through the canonical Hartree-Fock equation, we have many orbitals, and in principle their number is infinity. N of them will be used in Hartree-Fock, of course. The rest of them will all be called unoccupied orbitals. Usually they will be higher orbital energy than the Hartree-Fock orbital energies. Okay, with Hartree-Fock is the ground state. So that is the lowest energy. So usually these will be all higher energies. The lowest of these are what is called LUMO. The highest of these is what is called HOMO. Those who are already used to HOMO and LUMO will now appreciate that among the unoccupied orbital, this is the lowest, because I have ordered accordingly. Among the occupied orbital, this is the highest. So this is called the HOMO, this is called the LUMO, and they have a very interesting chemistry to play, because the energy difference can be very small, can be large, and depending on that, lots of interesting chemistry takes place. Okay, we already know that. So the unoccupied orbitals have a very important role in quantum chemistry of electron correlation, but even more important, even before that, we will see that they have a role even within the Hartree fog. And what is that role that we will see? Now, what happens if these two become degenerate? Of course, those are the questions. Then there will be a lot of problems. Well, that's basically the multi-reference problems and so on. We'll see that later. Yes? We never find, but in principle there. We will see. Huh? How do you know which are the lowest energies? After you get the energies, just find out which is lowest. That's unimportant. I can find out for any operator eigenvalue equation, even a finite value them, not all. I can still order them, right? As long as they are greater than m, there will be unoccupied orbitals. As long as the number that I find out is greater than capital N, then I can order them and find out some of them unoccupied orbitals. So if you are asking how do you solve this, yes, there is a way to solve all the spin orbitals. In fact, numerically one can solve for atoms very easily. No. What I am trying to say that numerically you can solve all the spin orbitals. What you are essentially saying is that maybe the lowest spin orbital is missing. That's what I am saying? No. Numerically, there is a procedure of finding the lowest energy, the second lowest energy. So that is the eigenvalue equation. Okay? And for molecule, of course, we use what is called the basis set. So we got a matrix eigenvalue equation in which we exactly will know how to again get the lowest energy. So there is a way to find out. Okay? So right now, let's not bother how do we find out. Let's assume that we have the energies which you can order. And these are the final energies. Whatever energies you have got, we can order them, and then we can call these unoccupied orbitals, and you can call these occupied orbitals. So there are two subset of orbitals we are defining. One is called occupied orbitals. What is the number of occupied spin orbitals? Always n, right? Number of unoccupied orbitals will be very large, in principle up to infinity. Okay? Depending on how many you can find out. So that there will be a lot of approximate ways of find out, but in principle they will be very, very large, and in principle they will be infinity in number. Okay? But this number is always capital N. So, and this then we can now relate an important theorem again by Koopmans for electron affinity. Before I tell electron affinity, can somebody tell me how to define electron affinity? What is the definition of electron affinity? Okay, of course you can tell energy that is gained if in a system have an electron, etc., etc. But can you tell me in terms of n electron energy and n plus 1 electron energy? What is it? Just like I wrote for IP. No, don't worry about Hartree fog. It can be any approximation. Just write En. So what is electron affinity? En minus En plus 1. Okay? Is it everybody agrees with this? If n plus 1 electron energy is less than n electron, then it is stable system, and then we say that the electron affinity is positive. So positive electron affinity means n plus 1 electron energy is actually lower than n electron energy. That can happen many times. Okay? Normally you may think that it is higher energy, so how it will become negative? But it can become lower because this energy orbital energy may become negative. So when I put an additional electron here, the energy may actually go down, and it happens many times. In fact, that is what is exactly told in the Koopmans. So this is electron affinity. So the Koopmans approximation says that if I now exactly do the reverse of what I said here, if I put an additional electron in this system, that means I generate a n plus 1 electron thing. So first Koopman is saying, let me generate a n plus 1 electron wave function such that I have all chi1, chi2 to chi-n, and then I add an additional chi-n plus 1, or let us say chi-r, where r is outside. So r is in the n plus 1, n plus 2 set. So one of them. Okay? R is in this set of n plus 1, n plus 2 to infinity. So I add an electron, I add a spin orbital rather, which means now I am defining an n plus 1 electron determinant, Of course, this chi-r can be anywhere, it does not matter, that is not important because they are all anti-symmetrized. Then Koopmans says that the electron affinity in Koopmans approximation can now be called as minus epsilon r. Just like I said minus epsilon j, the electron affinity will be minus epsilon r. So again, it is very interesting what I said. If this energy is negative, what is minus epsilon r? That is positive. So electron affinity is positive. So in a very simple way, you already know this. If a LUMO is a negative, then you know that one can put an extra electron. Electron affinity becomes positive, and that is exactly what is seen in this Koopmans approximation by saying minus epsilon j or epsilon r. So again, the proof goes exactly in the same manner. If you can do that home assignment, it is exactly identical, except that here there one missing, here one addition. So when you do the summation, you have to remember that you have to add an extra chi-r, okay, or chi-n plus 1, whatever. You can take LUMO chi-n plus 1. Again, this works very well. It works well if R is a LUMO. Okay, I hope you understand what I mean now. That means R is n plus 1, just the next one. If you put it at very high energy, it does not work so well. That is one. The second is that you have two Koopmans approximation, one for IP, one for electron affinity. So Koopmans IP is better than Koopmans EA. Between these two approximation, IP works better than electron affinity. If you compare with experiment actually, final result. So the electron affinity doesn't work so well. Remember, first of all, there are lots of approximation. That Hartree-Fock itself is approximation. Koopmans is a further approximation. So the two levels of approximation we are using, and we are saying when I compare with the experiment, that is exact to exact. In that case, IP works better than the electron affinity, and I will show you by a simple bar diagram why it happens. Okay, and why electron affinity gets actually worse. So I can also define electron affinity Hartree-Fock by the same way as defining En Hartree-Fock or SCF minus En plus 1 Hartree-Fock. In which case, of course, everything will change. So it will no longer be Koopmans approximation. All the spin orbitals will change if I do Hartree-Fock. So that's a completely different ball game. Okay, are the statements clear? The most important part of the statement is, of course, let's say for IP, is not this. This is an algebra. The most important part of the statement is something which is not said, which has not been discussed. Many times unstated things are more important than stated things. I hope you know that. I mean, those who know literature will appreciate what I am saying. That the unstated things are all. What is unstated? That is, this is an approximation which Koopmans said works very well in the first order. And we are not discussing that. If I assume this, the rest is algebra. What you are going to do home assignment is an algebra. Koopmans, this cannot be such a celebrated theorem. It is just application of Slater rules and doing plus minus. Anybody can do that. The original Koopmans theorem was to show that these n minus 1 spin orbitals, or for electron affinity the n spin orbitals, can be assumed to be the same to the first order. So you are not making to an energy second order. Actually, wave function first order, energy second order. That's another issue. That the perturbation, you know, that energy always goes one order higher. Okay, we'll show this. So this is something that was important part of the Koopmans approximation, which is always omitted in all textbooks. In fact, in the textbooks they never discuss this. That why the Koopmans. So Koopmans actually used a variation method to show that if you do this, you are only making an error beyond first order. Of course, this is an error, this is an approximation, but the error is only beyond first order, and that was the main content of the Koopmans approximation. The rest is history, because if it is so, it is going to be so. What is so great about that? Because this is only an application of Slater rule. Koopmans cannot get credit out of this. So this was a real Koopmans approximation of application of variation method and analyzing the error bar. That is the most important thing. Thalia Koopmans, 1931, he did this approximation, and the story about Koopmans that I have told in many classes, that eventually he applied the same variation method in economics. Economics has a lot of variation, as you know, the market, stock market, etc. And 1935, he got economics Nobel Prize, actually applying the. Koopmans did not get a Nobel Prize in chemistry, in fact. He found that quantum chemistry is too crowded, there are a lot of big people. So this was not big enough to get Nobel Prize, okay. So but he applied his knowledge, and that is very important, domain knowledge, into a field of economics. How does stock market vary? It's the same variation method, remember, stock market. Euler variation, all that he applied, and then he showed that to second order how much will be your loss if you invest. Always remember this, that you can do a lot of things provided you know how to use your knowledge, sometimes beyond your domain, because the skills are same. Okay. For example, when you do matrix eigenvalue equations, lots of interesting things have been done in quantum chemistry. Most of them are done long back by engineers or by mathematicians. Matrix problem is, they have been applied, and lots of new things have been done, new approximations have been made in quantum chemistry. Similarly, somebody in quantum chemistry goes out and applies this to economics. So Koopmans is a very interesting example. And also remember the name of the Koopmans. Again, a lot of people make mistakes, so I want to make, this is the name. So when you say Koopmans approximation, the apostrophe comes after S. Okay, blah, blah, blah. I want to make sure that you don't write Koopman, then apostrophe. Yeah, his name is Koopmans. So when you say Koopmans S, there is no other S, so you just have apostrophe. Okay, so that you know in English. So I just thought I'll correct this. Actually, the name is Koopmans, Thalia Koopmans, and so it is called Koopmans approximation. So please remember the small errors, because many people make this error, so I thought you should not make. Okay, I will come back to this point, and I will actually show why did I say that for IP it works better with a bar diagram, and then we'll move forward.